Session. And today our speaker is Professor Andrey Pilipenko. Andrey, please.
Okay. Today I will talk about diffusions in cones and cylinders. And one of the main subjects, one of the main questions is the following. Assume that we have a diffusion in some cylinder with reflection at the boundary. And the problem is the vertex hit? So let me say about a few words about motivation and about papers on this topic. And what does it mean? Stochastic differential equation with reflection. At first, let us consider a cylinder in d-dimensional space, and we assume that the boundary of cylinder is smooth, say C3.
A cone, not a cylinder.
Oh, not cylinder, a cone. Excuse me. Thank you very much. And if we consider intersection of a cylinder with a unit sphere, then this surface is a set D. So this is D, and D is smooth. And we assume that there is a vector field, say C of x at the boundary of this cylinder, and C is also smooth, say 3 times continuously differentiable everywhere except of vertex. And at first, what is Brownian motion in a cone with reflection at the boundary? I will denote boundary D. Reflection diffusion, reflection Brownian motion is a solution of the following stochastic differential equation. dxt is dw of t. This is multidimensional linear process plus c of x of t dl of t, where L is continuous adapted process, non-decreasing. L of 0 is 0. L is non-decreasing, and L may increase only when this process X hit the boundary of the cone. This means that integral of x of s, integral from 0 to x of s belongs to boundary. dls is L of t. And we always assume that C, this vector field C, points inside the cone, and the scalar product C of x and n of x, and this inner normal vector, is always 1. It is known that there exists a unique solution to this. Excuse me, and I forget. And x of t must be inside closure of this cone. So it cannot exit outside. So this,
is it a additional condition?
yes, this is additional condition. Exactly. This is additional condition. And this non-decreasing process L.
Sorry, but D, it is the whole cone or the cone up to this intersection with the sphere?
No. Oh, not D. Excuse me, Yana, thanks a lot. D is intersection, K is cone, and this is boundary of the cone. Yeah,
okay.
Sure. Thanks a lot. And X should be inside the cone. So this process behaves like a Wiener process. So its increments are increments of Wiener process if the process is inside the cone. Yes.
Then in your equation, this intersection with the sphere does not appear at all. Yes.
No. I will use this set D maybe later, and I will say that this set D has a smooth boundary.
Okay, but at the moment we don't need it. So the process is there. Okay.
No.
I'm sorry, I have another question. DLT, you said it is a non-decreasing process.
Non-decreasing.
But in which sense? Because we have like multi-dimensional picture.
No, one-dimensional. L is one-dimensional. C is a vector. C is a vector field.
Oh, I
C
see.
is a vector field. It points inside this cone.
I see now.
And when this diffusion hits this cone, this process L grows somehow, and this term pushes the diffusion inside the cone. But when diffusion is inside, there is no effect of this. L do not increase. So L may increase only when you hit. And it is known that there exists a unique solution to this equation up to the moment when this diffusion possibly hit the vertex. And the question is how to find the probability that the vertex is reached by this diffusion. And a very interesting question is it possible to find a solution to this stochastic differential equation for all t, not only for the moment of hitting zero, but is it possible to exit from the vertex and then the process should satisfy this stochastic differential equation? The first result on this topic was obtained by Varadan and Williams. In 1987, they considered two-dimensional case. So we have just wedge, two-dimensional wedge. And they considered vector field C of x such that C depends only on the angle. So here the vector field is equal to some constant C1, and here vector field is just a constant vector field C2. And they found necessary and sufficient condition that ensure that the vertex is reached by the reflected Brownian motion. And moreover, they found necessary and sufficient condition of existence of a strong Markov process that behaves like this diffusion everywhere outside of zero, and spends 0 time at 0. For example, the necessary and sufficient condition that ensure that diffusion hits 0 is the following. Consider this angle alpha 2, this angle alpha 1. Okay, we assume that this angle is positive and this angle is negative. So if vector field C2 is this, then the angle also positive. So necessary and sufficient condition ensuring that the vertex is reached is alpha 1 plus alpha 2 is greater than 0. Later, results of Varadan and Williams were generalized by Williams and Kwon, who considered multi-dimensional case with a Brownian motion in a cylinder, and their assumption was that this vector field C of x depends only on polar angle. Depends on polar angle. Phi is x over absolute value of x. Well, phi is defined everywhere except of 0. And the main idea was the following. They found some non-negative harmonic function. And in terms of this harmonic function, they estimated at first probability that this, okay, if you start from this point, that you hit some level earlier, then exit another level. Well, such theory is well developed in for SDEs, one-dimensional stochastic differential equations without reflection. But usage of harmonic function for studying of hitting probabilities is quite natural. Then they estimated time that is spent in neighborhood of 0. They constructed the following process. If the process hit 0, if they estimated expectation of time of hitting 0, and then consider the following process. If you hit 0, then exit to some small number delta, then again exit to this number, then again and again and again and again, and then send delta to 0, prove compactness, and then for this process, again, estimate the time spent in this neighborhood epsilon, and send epsilon to 0. And if this time is very, very small, if this time converges to 0, they proved that there exists a diffusion that behaves like a reflected Brownian motion outside of vertex and exit somehow from 0. As I told before, their behavior was based on investigation of harmonic and subharmonic functions, but unfortunately there was no probabilistic proof. I mean probabilistic methods. And now I would like to show you some probabilistic ideas different from Vardan and Williams. And today I only answer the question, does diffusion reach the vertex or not? I can answer to the question not only for reflected Brownian motion, but also for some stochastic differential equations. At first, I consider stochastic, some special stochastic differential equation with reflected vertex reflection vertex field that depends only on an angle. But then I also explained how to do it for some small perturbations of this reflected vector field. And at first, let me make some preliminary calculations. And the idea is quite old. And Olga Ryasova and me use this approximately 10 years ago when we studied two-dimensional Brownian motion in a plane with some membranes with oblique penetration. And the question was, is this diffusion, does this diffusion reach zero or not? Okay, so what I'm going to study? Well, we have cylinder. I denote cylinder. I have vector field C that depends only on phi. Phi is polar angle. And let rho be, r be just absolute value of x. And rho be logarithm of r. And equation is dxt is dw of t plus c of, okay, let me write phi of t d L of t. And I would like to rewrite this equation in polar coordinates or in log polar coordinates. Well, a little bit later, I will rewrite it in log polar coordinate. But if you consider a transformation rho phi, and if x belongs to this cone, then rho phi belongs to cylinder R multiplied by this set D. This set D. Intersection of a cone and a unit sphere. And if x converges to 0, then rho converges to negative infinity. Well, I would like to apply Ito formula, and let me write down. Okay, generator of Brownian motion is 1/2 times Laplacian. And if you write Laplacian in polar coordinate, then you'll get well-known formula plus d minus 1 r to the raised to the power -1 d over dr plus this, and this is Laplace-Beltrami operator. Well, this is operator, second order operator, differential operator that depends only on phi. I will not write exact formula right now. And I would like to write this operator in terms of rho. And this operator can be also written as follows. This times r d over dr squared plus d minus 2 r d over dr plus Laplace-Beltrami, and r d over dr is just d over d rho. Okay. And if I apply Ito formula, and if I make some transformations, then I obtain the following as dE for radius and for polar angle. So let me write it. D rho t is equal to e to the minus 2 rho t, then d minus 2 over 2 dt plus c tan. I will explain what is a c tan, tangential component of this vector field c, of phi of t dl of t plus e to the minus rho t d some one-dimensional Brownian motion. Let me denote it by b rho of t. Okay, let me show you previous step, and please look here. Second derivative with respect to rho and d minus 2. Well, and that's all. And equation for phi is this: d phi t is equal to e to the minus 2 rho t d c. Excuse me, here another component, phi of t dl t plus db phi of t, and this is Brownian motion on a unit sphere. On a unit sphere. And what is these two components? We have a vector field C of phi. And we have this intersection with this sphere, and we represent this vector field as a sum of two. See tangential of phi, and this vector field belongs to tangential plane and normal one, and normal is parallel to this line plus c, and I will call this vector field radial vector field. So this radial vector field is just scalar product c phi times phi, and this is difference. They are orthogonal. Oh, excuse me, I made a small typo to the minus rho of t here. And you see this term, if we delete them, okay, let me just cancel them for a while. Then what do we see? We see just diffusion on a sphere. And what is this? This is just a process. This is just a Brownian motion.
But the equation for phi is not equation for diffusion because the scale depends on rho.
Yes, yes. I say for a while, let me delete this term with rho.
No, not with rho. L also depends on rho. Yes?
No, I will explain you that not L. I will explain you that L. L
is the okay. That's from phi. Yes, because phi is.
Yeah, we will discuss a little bit later. Okay. Yes, you are absolutely correct that formally L depends on rho. But you will see that not. And really, let's look at this equation. Phi belongs to D. Phi of t belongs to this part of a sphere always. This L hits this L may increase only when phi hits boundary. So if we delete these two terms, we see just a diffusion on a part of sphere on some domain, on a manifold, with reflection at the boundary. So actually, L will depend only on phi. And we see just two terms, dt times some constant, and now some additive functional of phi. But how can we delete? I say, assume that we delete. It is not so honest way to prove the theorem. And let me make a transformation of time.
Sometimes it's useful, yes?
Yes, let's make the following transformation of time. A of t is infimum of s such that integral from 0 to s of these e to the minus 2 rho z dz is equal to t. And let me denote by rho with tilde t, rho of a of t. And phi tilde t is phi of a of t. And this is traditional. So this is additive functional. This infimum is inverse. And rho tilde phi tilde. So rho phi is a Markov process. When we use this change of time using additive functional, we obtain again Markov process. Actually, we had homogeneous Markov process, we obtained homogeneous Markov process. And a new coefficients are the following. You delete this by this, so equation is this. And coefficient near Brownian motion is divided by square root of this. Actually, we have another Brownian motion. This Brownian motion can be obtained from B rho using some transformation of time. And again, we don't have this term, we don't have this term, we have this equation. So what do we have? Really, we have a pair phi tilde that satisfies stochastic differential equation in a manifold with smooth boundary dw phi of t plus c tan phi tilde with t dl of t. Actually, there will be another increasing process. So I should write here with some tilde. And this L with tilde can be obtained from L using some also transformation of time. But we had increasing process, we got increasing, non-decreasing process. And the rho tilde of t is dw rho t plus d minus 2 over 2 dt. Excuse me, this d is dimension and this dt is the differential, and plus c normal. Oh, yes, c. No, this is normal. This is radial. Sorry. So this is tangential, and this component is radial component of phi of t dl t. And I can also return from this process to the previous one. And the transformation looks like this. I only have to consider the following function, infimum of s greater than 0, such that integral from 0 to s e to the plus 2 rho tilde z dz is t. And I told you that if rho converges to minus infinity in this new time, then rho without tilde converges to vertex in real time. Oh, no, rho converges to minus infinity in real time. And radius, or this diffusion, converges to vertex. And the question, is the time finite or infinite? Well, you may you may have convergence here, but after transformation the time, maybe you only asymptotically go to vertex. Maybe you don't reach it. However, I will show you that if you go to negative infinity, then rho of t is equivalent to some negative constant times t. And if you do this transformation of time, then you see you have integral of e to raised to the power something, which is approximately linear function, negative linear function. Then we will see that after inverse transformation of time, you hit vertex infinite time. And now let's consider general stochastic differential equation. Assume that we have two processes, x and y. The process y is the process with reflection in a domain D, so yt belongs to D, where D is some smooth manifold or just smooth set in Euclidean space with a set with smooth boundary, and D is bounded set. And x of t belongs to R. So the pair xy lives in a cylinder, and coefficients are invariant with respect to shift, with respect to x, with respect to horizontal line. And the question is, please find the limit x of t divided by t. And I will show you that this limit is a constant almost surely, and I will explain you what is the constant. I will find this constant. And when we return to diffusion in a cone, then the result will be the following. If this constant negative, then you reach vertex in a finite time with probability 1. If it is positive, then, or if it is 0, then you never reach. Well, okay, I will not discuss the case when this constant is 0. If it is positive, then it never hits the vertex of a cylinder. And assumptions on coefficients are the following. They are smooth. Say C3 coefficients. This vector field V points inside this set D. Okay, so this is V.
Okay, Andrey, let me ask you, this Y is a diffusion inside this domain D.
Yes.
Yeah?
Mhm.
Okay, so maybe it has some invariant distribution, yeah?
Yes, sure. Exactly.
And then this is a law of large numbers for X, yeah? For
Yes.
W. For W.
This is the law of large numbers. Yes, exactly.
I see. Interesting. Okay.
And my assumption also the following. I assume that, okay, let me check, that this B is non-degenerate in the following sense, that if you take Y and consider the sum and consider this matrix, then this matrix is uniform, satisfy hypoellipticity, uniform ellipticity property. The constant C is greater than 1, I is identity matrix, and I demand this for all Y in D with the same constant C. And this is true. It is known that if we have this, if all coefficients are smooth, then Y is ergodic Markov process. Then Y is ergodic Markov process. And we have mixing, well, very good mixing properties, and even moreover, I can write stationary distribution, okay, for the process Y of t. It satisfies some elliptic equation in D, so its density, with some boundary conditions. So there is explicit formula. And we have exponential mixing. What does it mean? That if you have two solutions started from point, say, y1 and y2, and if we consider distance in total variation between this distance is less than constant time e to the minus lambda t, where this constant is independent of y1, y2, and lambda is positive number.
This is proved in this paper of Kant and Ramanan.
No, not.
What will be the good reference? Because this is my own interest, not related to Kant.
Okay, we did it and we proved. So let me explain you the idea. So we didn't find exact reference, but the proof is the following. It can be proved with a probability separated from 0. You may find some time positive, okay, for there exists tau. There exists positive probability such that the process y of tau separated from the boundary by some small distance, say delta. So this distance is delta. This can be proved just using stochastic differential equation. The second step, if you have 2 points inside this domain, then before you hit the boundary, you behave like diffusion. For diffusion, you have estimates of transition probability density function even for killed diffusion at this boundary. And you can show that, well, there is some domain that you say in time tau, you will hit this. The distribution of the transition probability density is separated from zero. For usual diffusions, it's well known, and for Kiel diffusions, it's well known. And then you apply some technique related to coupling and doubling condition. So in positive time, diffusion can enter some domain, and transition probability density is separated from zero. Then you coalesce, and then you made a lot of iterations, and then you get this estimate. Or another solution is the following. You have to
Okay, Andrey, thank you very much. I understand how to prove it. I only asked that you also didn't find the reference.
No, unfortunately not.
Because I remember that Vretennikov did a lot on the mixing condition for diffusion process, but without reflection, I think.
You see, you have to write this equation with reflection, then you have to write some properties of transition probability density function. And theoretically, this transition probability density function satisfy Kolmogorov equation, some parabolic Kolmogorov equation with some boundary conditions. And I believe that it's written that this density, some a priori estimates from below.
Yes, even Mark Katz did something for bounded domain. He wrote that particle did not know that they will be killed at the boundary. So inside of domain we have Gaussian estimation. Yeah. Okay. Thank you very much. I understand the reason, and it is expectable that Y has ergodic behavior with mixing.
Yeah,
so now we can go to X. Yeah.
Yeah. Now we go to X, and we write X in integral form, and we have three terms. X0, okay, for X0 plus this. We divide X by T, and let's discuss every term. The first, X of 0 divided by T converges to 0. The second is just a law of large numbers of additive functionals of a Markov process with nice mixing. And what is the limit of this? Just integral of this function with respect to stationary distribution. Now, what is this term? What is this term? This is martingale. This is martingale, and its square characteristic is integral from 0 to t sum of bk squared y of s ds, and this is less than some constant, say k times t. And it's well known that behavior of m of t is less than t. Moreover, it's less than t raised to the power 1/2 plus delta for any delta greater than 0. Because this martingale is a transformation of a Brownian motion. And this function does not increase too fast. And for Brownian motion, we know the law of iterated logarithm, so this converges to 0. This converges to 0. And we have the third part with the local time. And this is the most interesting part. And let me explain you how to work with this additive functional. At first, let me find a function such that gradient of f times v, and let me recall you that v is this reflected vector field, is equal to gamma. And we want to estimate this gamma DLT. It can be shown that such vector field f, such function f exists. Moreover, there are a lot of functions f that satisfy this condition at the boundary. And f may be arbitrary inside and outside, so no conditions at all. So just some relation at the boundary. And now let's write eta formula for f of y of t. What do we have? Generator of f of y of t plus term with Brownian motion plus this term. And what is this? This is gamma of y of t. So integral of gamma of y of t dl of t is equal to f of y minus f of y of 0 minus this. And now divide this by t. And let me recall you that domain is bounded. So f of y is bounded. F of y of 0 is bounded. So this converges to 0. This converges to 0. Everything is bounded here. So this martingale divided by t converges to 0 almost surely. And for this term, we have the law of large numbers. But you see, I want to have the law of large numbers of gamma of y of s dls over t. And I can obtain the result in terms of this additional function f. I would like to obtain result in terms of this vector, in terms of function gamma. Okay, the law of large numbers applied to A is this. We have this. And then we have to use integration, by parts. And there was a formula obtained by Kang and Ramanan. And if you do this, you obtain this integral with respect to the boundary, and dsy is a surface measure. And then we recall that gradient of f times v is equal to gamma. So our result is in terms of gamma, and the theorem is proved. So we know how to. So we know the law of large numbers for this process x of t, and the only non-trivial term was this, the term with local time. Actually, such pairs are called sometimes Markov additive process. One coordinate is a Markov process, and another coordinate, well, its behavior depends not only on position x, it depends on the first process y, on the first process y. And the next question is the following. Assume that you have a perturbation of our original equation. So so we consider process in a cylinder with a reflection and assume that coefficients for this SDE are close to alpha, to V, to all that coefficients from the previous theorem. Certainly, there is no law of large numbers for x epsilon over t. And I would like to find some deterministic bounds for this upper limit of xt divided by t and lower limit x epsilon of t over t. And the result is following. If coefficients alpha, v, and so on and so forth are smooth enough, boundary of D is smooth, function f and function g are also smooth enough, then there is a universal constant c that depends on the function Lipschitz constant of f, coefficients alpha, v, gamma, all other coefficients, such that we have the following bounds. So C is non-random. C is non-random. So if epsilon is small enough, then you have the following relations where A1 of f and A2 of g are the same as in previous theorem. For example, what does it mean? This means that if alpha, v, and so on and so forth are such that the process x of t over t converges to some constant which is positive, then the process x epsilon will converge to plus infinity, and we can say that it grows is has a linear growth. So we can estimate lim inf and lim sup by some constant plus or minus this small number. Actually, this number is small if epsilon is small. And if x of t converge to negative infinity, then x epsilon will converge to negative infinity. And the growth will be also linear. And if so, one of the corollaries is the following. If you have a diffusion in a cone whose coefficients are close to coefficients that depends only on phi, and if a diffusion with coefficients that depend only on phi hit vertex in finite time, then a diffusion with little bit perturbed coefficients also hit zero in finite time and actually with probability 1. With probability 1. We have a dichotomy. If this constant is positive, then never hit with probability 1. If it is negative, we hit infinite time with probability 1.
I'm sorry, I have a question.
Yes.
How do you make a conclusion that the time is finite?
Because of inverse time change.
But oh,
So let me find, I didn't write. So the time change, the time change was the following, inverse time change. A of t is infimum of s such that integral from 0 to s e to the, well, I had the function rho with tilde, but now it is x.
mhm.
It was 2 rho tilde z dz is t. And our process, the radius r of t or x was this, or excuse me, this logarithm of was rho in this time, a with tilde of t. And we know that rho tilde of z is equivalent to some constant, say a times t or times z, as z tends to plus infinity. If this constant is negative, then the integral from 0 to infinity e to the 2 rho tilde z dz is convergent.
Yes.
And if this integral is convergent, and what is the hitting time of 0 or for transform process? This is first time when okay, we find rho with tilde, and rho tilde converges to infinity, and infimum of s
So I think we can skip for a moment because it's going to be published, right?
If
Yeah.
rho converges to minus infinity, yes, then this integral converges to finite.
yes, then this integral converges, yes,
But it converges and
almost surely for omega, for almost every omega.
yes, but it's like minus infinity is not reachable in this model. And
Yes,
0 is that
yes,
is reachable, so it's
yes,
not like
minus
1 to
infinity
1.
is reachable, yes, but this is slow time. But when you make this transformation, then this time is faster and faster and faster and faster. And
Yes,
this time converges to negative infinity. And in this transformed time,
I mean, this model are kind of equivalent up to the heating time.
yeah, exactly, up to the heating time. And heating time, yes, what is the heating time for and heating time for the process in a real time is is supremum. Let me write this epsilon, sigma epsilon, where sigma epsilon is the time when you hit epsilon, and then you send epsilon to zero. Yeah, actually, yes. Actually, we don't know how to solve our initial equation when you hit the cone. We don't know. You can you can solve the problem if you in every domain.
So you can get to every
is,
neighborhood of zero.
Yes, in every neighborhood of zero. Yes, and what is hitting time of this part, or you can consider smooth, even smooth, is clear. And then you send this boundary to zero closer and closer and closer, and heating time of this is finite and is bounded by the same constant.
Because
by the same constant, yes, because the integrals are convergent.
Thank you. I think I understand.
And
This is the
when
main
you
idea.
yes, and when you hit this and this and this and this and this, yes, then you here it will be like these boundaries. You hit this and this and this and this, and you hit these boundaries in real life, in real time, and you see that the limit is finite. And let me also mention that the process converges to negative infinity. So you don't reach like this. Hit, maybe exit, walk, and then hit, and then exit. No. You have really limit. You have a really limit here, so you have really limit here.
I see.
So limit of this x of sigma epsilon are epsilon to zero is really zero. Is the limit exists.
I see. Thank you very much. Thank you.
Andrey, you are disappearing.
Hello, no, I'm here.
You are here. Okay,
Your screen is off.
Oh.
Okay, so do you continue, or this is the end
No,
of the
that's all of my talk. Well, unfortunately, the proof of this result is very, very long, and it is not based on some comparison theorems, because we don't have monotonicity for these perturbed stochastic differential equations. We used some coupling methods with stationary processes, some estimates for martingales, and so on and so forth. So this theorem is some analog of law of large numbers for some inhomogeneous Markov process. So this is law of large numbers for additive functionals of non-homogeneous Markov process whose coefficients are close to a homogeneous Markov process.
Okay, thank you very much for such interesting and complete asymptotic analysis. Maybe somebody have comments or questions, please.
Or maybe one more remark, that I would like to find probabilistic proof of Varadhan and Williams and Kwong result some necessary and continuous conditions proved by Varadhan and Williams and Kwon of existence of a diffusion that behaves like a stochastic differential equation inside a cone, hit vertex and exit from vertex. And I hope that I can use this pair of in log polar coordinates in slow time, in a slow time, without appealing to some subharmonic or harmonic functions.
Okay. Yes, it seems that you can define this Markov process on the all real line with some law of interest, yes?
You see, there is no problem before you hit with the vertex. But then a question, how do you exit
Yes,
from
yes.
the vertex?
I'm just saying about this equation on the all line.
Mhm.
And I think that maybe you can use some law of interest for this.
But the question is, so you exit from negative infinity.
Yes, yes, yes.
It is not clear. You sometimes you can exit, sometimes not. Sometimes there is a diffusion that hit and exit, but sometimes if you hit, you cannot exit, you stay at zero forever.
Mhm. Yes.
And actually, it is not a problem to prove uniqueness of the process if it exists.
Mhm.
But existence is a problem. So it is a problem to prove that there is a process that exits from zero or from negative infinity.
Mhm. Mhm.
Because you see, when you push to negative infinity, maybe this push is so strong that you cannot exit.
Yes, yes. Mhm.
By the way, these processes are maybe very bad. For some reflections, they are semi-martingales. For some reflections, they are still continuous Markov process, but not semi-martingales.
Mhm. Oh, I remember you said something about this.
It is like Bessel process. Sometimes, so Bessel process is a diffusion, continuous Markov process, but sometimes Bessel process can hit zero and exit, and it is a semi-martingale, but sometimes you can hit zero and exit. Bessel process is not a semi-martingale, and sometimes you hit zero and never exit. So the same picture is here. And Varadhan and Williams, they considered only Brownian motion, but it seems to me that it is okay. It's my dream to find probabilistic approach for diffusions whose coefficients depend only on polar angle.
Okay, thank you. Some other questions, please.
I have a remark that you were talking about like the possibility of entering from infinity, but it's not a priori clear that this model, transform model, and the behavior of the transform model, the original model, are the same in this sense.
No. Well, it is not good to talk about processes that enter from negative infinity, because if you hit in negative infinity in finite time, then any extension will be discontinuous. But entrance to cone from the vertex is related somehow to entrance from negative infinity, but with transformation of time, with some transformation of time.
I see, thank you. And also,
Okay.
I have a small remark that I have this paper asked you to send me, but only read the calculation part that was relevant for me. I didn't read the rest. I'm sorry still.
Okay. Other questions, please? Okay. If there are no any questions or comments, thank you again. And we can ask Georgi who will be the next speaker.
The next speaker will be Mykola Vovchansky.
Okay, good. See you next week. Bye.
Thanks. Goodbye.
Bye.